Lesson 9, using a curve to model a data distribution, is going to pretty much pick up where we left off with Lesson 8. So this content is going to seem the same. We're going to talk about curve and standard deviation and mean. It's just in this case, we're going to actually get a chance to draw some of those models in this one. So you'll see that with two examples. This one right here, which we'll talk about, this little old dinosaur right here called a compy. I don't know much about it, but there's a picture of it. And then we're going to have example number 2 that we'll look at as well. So in this one, we have the heights of the dinosaurs in a normal curve. A paleontologist says they studied the prehistoric life of some of these dinosaur fossils. The table below shows a distribution rounded to the nearest inch of 660 of these dinosaurs. The heights were determined by studying the fossil remains of the compies. So what do we see in this design? We see the different various heights that were measured, the number of compies that came in at such height, and then the relative frequency of each one. We note down here in the blue box, out of 660 total, that were number of compies total, and we use that to help us get our relative frequency each time. So 1 divided by 660 would be the 0.002. 5 divided by 660 would be the 0.008, such that if you did 660 divided by 660, you get 1. So this is the data that we're going to model off of and use this to study some of the same content we did last time. So if we look at exercise number 1, it starts off with the following is a relative frequency chart that shows the history of the compy heights. Number 1, what does the relative frequency of 0.136 mean in terms of the height for these particular dinosaurs? So if we looked at that, 1.366 would be generally about right here. Notice that lines up with the top of that bar. And if we were to scroll down and take a look, that would take us to 32. So this is what we're looking at and measuring in this design. So again, the question is, what does that relative frequency of 0.136 mean? And so that is telling us that 13.6% of the 660 dinosaurs that were measured were 32 inches tall. We follow up with what is the width of each bar and what does the height of the bar represent. So if you were to measure, and mine's a image, but each bar has a width of 1 centimeter, and then the height of the bar is the relative frequency for the corresponding height. Now, the reason why they set it for 1 centimeter is pretty relatively simple, and we'll look at that at another example coming up. But 1 centimeter from piece to piece, so if I made a mark between here and here would be 1 centimeter, this would be another centimeter, this would be another centimeter, and then the height up is the relative frequency that matches, of course, right there, and of course right here you see in this diagram they say the height is measured, or the width, each one is measured in centimeters. So that's another indicator mark for that. Number 3 says, what does the area of the bar represent for the relative frequency of the compies at a height of 32? And so if we look at that, the area of the bar is equal to the relative frequency. And really what they mean by that, if I was to take this bar right here, and let's just say we colored it, and I asked you, what is the area of this? Now let's take the obvious thought here, right? Geometry. If we noted that the width from here to here was the length of 1 centimeter, and we measured the length from here to here all the way down to the bottom, that would be the length and width of a rectangle. And so that would be the area of this rectangle right here, 1 times however high we go. And so that would be 1 times 0.136, and that would be the area of that bar. That's one of the reasons why they chose every width of this bar to be 1 centimeter, if you're looking to put a good reason behind it. Continuing with number 4, it says the mean of the distribution of the compy is 33.5. And so if we made note of that right? 33.5. There's 32. 33.5 is somewhere around this area, and the standard deviation is 2.56. Interpret the mean and the standard deviation in the context of the problem. So when we look at that, we note that the mean, which is 33.5, is the average height of the compies in the sample. And then it can be interpreted that a typical compy height, the standard deviation of 2.56, is the typical distance that a compy height is from the mean height. Meaning how far left or right from the average is still considered normal. Meaning that would be considered acceptable in this design. So they ask us in number 5 to take that mean and mark it on the graph. So we could do that, right? We said it was 33 and a half, and so it would be 32, 33 and a half would be somewhere like right around here. And so we'll make that note, we'll call that 33 and a half. And it says to mark one deviation above and below the mean. This would be the standard deviation. So remember in the previous one we said the standard deviation was 2.56. So if we wanted to note that, right, what we would do is we would take the 33.5 and then we're going to add the standard deviation, which we said was 2.56. So we would add 2.56. And if we did that, that would be somewhere over here. And that would be this line right here. And so that would yield us 36.1. Same thing if we took the 33.5 and we minused 2.56, we would get the standard deviation in the other direction, which would be this location right here. So again, our goal in 5 was to mark the mean on the graph. We did that. Mark one deviation above and one deviation below the mean. Then they ask us approximately what percent of the values of this data are within one standard deviation. And so I think I got that hidden underneath here. And so we'll erase some of this out of the way now that we've seen that. And then we'll uncover this. And so what these numbers are, we'll talk about this, is the sum of the different heights. So if we looked right here, we'd have this one right here, which would be the 0.091. We would have this one right here, which is the 0.136. You got this one right here, which is 0.152. 0.152. This would be another 0.136. And this would be another 0.091. These would be the bars that fall within between the lowest standard deviation and the higher standard deviation. We add all those numbers up and we get 0.7658, 0.758, or 75.8% in that design. And so then approximately what percent of the values of this data are within 2 standard deviations? Now 2 standard deviations would mean I would take this length right here and I would add another 2.56 to this side. And so this would go out to this direction. And if I subtracted another 2.56 this way, I get another piece in that direction. I'm not going to go through that process, but that answer ends up being about 94% of the data would fall within 2 standard deviations of each one in that perspective. So now in number 6, we currently have the mean and 1 standard deviation above and 1 standard deviation below marked. They want us to draw a smooth curve that comes reasonably close to passing through the midpoints of the tops of the bars on the histogram. And this does not have to be perfect, but pretty much what you're going to do is you're going to kind of take and you're going to try to draw a curve that kind of mimics and demonstrates the curve of this bar graph. Remember we talked about symmetric versus skewed, and so we would tend to have this curve right here they ask us to describe the shape of the distribution. And so the curve is bell-shaped and is approximately symmetric and or mound shaped. You don't have to put all of that info. Symmetric would be good enough, or you could say that's what's called a normal curve. That would be the same definition in design. And then finally ask us to shade the area of the histogram that represents the proportion of the heights within one standard deviation of the mean. And so if we did that, right, if we color that, what we're basically doing is shading all of the parts of the bar that is in between the deviations, the low deviation and the upper deviation. So here I am kind of just coloring in each bar. We want this bar. We would include this bar here. We would include this one. And then we would include up to here in between there. And so this would be the shading that would occur in each one. And so when we're done, this is what it looks like as a finished product. It says, based on our analysis, how would you answer the question, how tall is a compy? And so in general, a compy would say the typical height is expected to be between 31 and 36 centimeters. That would be considered a normal typical height for this particular dinosaur. So again, just to go back and reflect, because this is the type of product you're going to create. What did we do in this process? Is we took a look at the mean right here. So we did that. Then we had one standard deviation above, one standard deviation below. We drew a bell curve, or a curve that basically goes through the midpoints of each of the bars. That way we can create a type of curve. And then we went through and we shaded what was in between one deviation below and one deviation above. And then we use that information to illustrate what would be considered a normal typical height for this set of data. So that's example number 1, exercises 1 through 8. We're going to model one more set just so you can see the process go again, start to finish. And so in this one, example number 2, they're going to bring up gas mileage and the normal distribution. So without reading all of this, right, they're going to talk about a particular model car or something like that. For example, a salesman kept track of gas mileage for his car for over a 25-span week. The mileages are listed below. I'm not going to read them to you. There are 25 different numbers here, and we're going to use that to extract some data. So what I've already done for you is I put them in order. It says consider the following. You can see the numbers range from as low as 23 and as high as 29. Obviously, some numbers repeat. That's what we're going to use the frequency chart that we see at the bottom here for in a minute. But what they're going to ask us to do is to use technology to find the mean and the standard deviation of the mileage of the data. Now remember, if you don't have technology, the mean is you just add up all the numbers, divide by how many you have. The standard deviation, if you need to go back and review that, there was a slide at the very beginning of lesson 8, the previous videos up in there. You can go back and look at that, and then you can calculate the standard deviation by hand. Otherwise, if we're going to do this by technology, the process would be, and if you have your graphing calculator, this is how it would be done. We would put in the stat key. We would press edit. We would enter all of our data into list 1. We would then press stat, select calculate, and then go to one variable stats. You're going to press enter on the word calculate, and that's going to calculate a whole bunch of numbers for you. You're only actually looking for 2 numbers. One of those numbers is the one that looks like this. That's our average. And then the S of X, which is going to be our standard deviation. So I would recommend you take a moment, and if you have a graphing calculator or any kind of technological means, try and see if you can find the standard deviation and the mean, and then unpause the video and then see if you got it right or wrong. Okay, so assuming you've done that, you should have gotten an average of 26.04, and you should have gotten a standard deviation of 1.5. 4. We're going to use those two numbers again to help us draw that graph in a moment. So to do this, we have to have a relative frequency chart, because that's what we're going to create a bar graph of. So we have to go through and count how many we got. So for 23, right, there was 123. It looks like there are 3 24s. There was 1, 2, 3, 4, 5 25s. 1, 2, 3, 4, 5, 6, 7 26s. For 27, we got 1, 2, 3, 4, 5 of those. For 28, we've got 2, and 29, we've got 2. That adds up to be 25 total. Remember, to get the relative frequencies, we would take the frequency and divide it by the total 25. So when we do that, we get 0.04, we get 0.12, 0.20, 0.28, another 0.20, and we're going to get a pair of 0.08. And just to confirm for fun, 25 divided by 25 is 1. So that's what we're going to draw a bar graph on when we look at that information. So in letter C, they're going to ask us to construct that relative frequency chart to make that match. So to do that, remember we said the dinosaurs for that was 0.04 for the first one. So if we did that, this would be a bar that would look like that. That would be 0.04. The next one would be 0.12, so it's going to come up to right there. And then slide down. Then we're going to have 0.20. So 0.20, right, is going to go there. And obviously, you know how to do this. You know how to fill in the rest. You could always take a moment and try and fill in the rest and then see if you're right or incorrect. But the other frequencies were 0.28, and then 0.20, and so on down. So we'll go ahead and color in the rest of the bars. Again, check your frequency table. Make sure yours matches. And then we get this particular shape right here. So this would be the first step in drawing that particular piece. Afterwards, let's see, this is part C. Part D, they want us to describe everything. And so draw a smooth curve. And so my bars went away. But you can see as I'm going, there's a smooth curve that is there, that is drawn over that particular piece. Describe the shape of the mileage distribution, draw a smooth curve that comes reasonably close to the tops. Is this approximately a normal curve? And we would say yes, this is approximately a normal curve. It looks symmetric, so that's kind of what we're generally looking for here. And then this last piece, they want us to mark the mean on the histogram. And so if we did that, the mean we said was probably right around here. So this would be our mean. We said that was 26. Let's see, what else did we have? We had our standard deviation. And if we went back and looked at that, right, our standard deviation was 1.54. So if we went 1.54, it would be a little over 27. So it would be like right here. So that would be our standard deviation on this side. And then if we did 26 minus 1.54, our other line would end up right there. These are the numbers that correspond with that. They ask us to then take and shade that information in between the standard deviation. So if we did that, right, we would end up shading in this bar here. We'll make this a little bit larger. We would end up shading in this bar. We would end up shading in this bar. We'll try and keep those green lines there for your visual sake. And then we would end up shading in this bar here to match. And so that would be the part that we would end up shading. So then they ask find the proportion of the data with one standard deviation of the mean. So if we looked at that, right, let's see what we got going on. We've got 0.20, that's this first bar. We've got 0.28, which is here, and 0.20, which is this bar. If we added them all up, that would be 0.68, or 68% of the data would fall between 24.5 and 27.5 in that particular data. So that kind of pretty much wraps up the piece of what we're going to do. That was the model. So go ahead and check Echo and see what problem set you're going to do for the week. And of course, if you have any questions, one, go back and watch the video so you can see the parts that you're putting together for me, and or give me an email if you have any questions.